Everyone, this is Papya Dutta, working as a lecturer in Devi Mahalakshmi Polytechnic College. I'm going to take a lecture on condition for oscillation and classification of oscillators. So here in this lecture, I'm going to talk about first the oscillator condition, what should be the condition, and after that we're going to discuss about the classification of oscillators. So first we'll understand about the practical oscillator circuit. So this is a practical oscillator circuit. So a practical oscillator circuit consists of a tank circuit. So this is a tank circuit, a transistor amplifier and a feedback circuit or feedback network. The following circuit diagram shows the arrangement of a practical oscillator. The parts of the practical oscillator circuit are: first one is a tank circuit, that is where L and C components are present. The tank circuit consists of an inductance L which is connected in parallel with the capacitor C. The values of these two components determine the frequency of the oscillator circuit, and hence this is called as frequency determining circuit. Next we will talk about the transistor amplifier. The output of the tank circuit is connected to the amplifier circuit so that the oscillations produced by the tank circuit are amplified here. Hence the output of these oscillations are increased by the amplifier. Next is the feedback network or feedback circuit. So the function of the feedback circuit is to transfer a part of the output energy to LC circuit in proper phase. So this feedback is positive in oscillators while negative in amplifiers. Now we'll talk about the frequency stability of an oscillator. The frequency stability of an oscillator is a measure of its ability to maintain a constant frequency over a long interval of time. When operated over a long period of time, the oscillator frequency may have a drift from the previously set value either by increasing or by decreasing. The change in oscillator frequency may arise due to the following factors. First, the operating point of the active device such as BJT or FET used should lie in the linear region of the amplifier. Its deviation will affect the oscillator frequency. Next, the temperature dependency of the performance of circuit components affect the oscillator frequency. The changes in DC supply voltage applied to the active device shift the oscillator frequency. This can be avoided if a regulated power supply is used. A change in output load may cause a change in a quality factor of the tank circuit, thereby causing a change in oscillator output frequency. Because if there is a change in the tank circuit, then there will be a change in the frequency. The presence of inter-element capacitance and stray capacitance affect the oscillator output frequency and thus frequency stability. So these are some of the factors which depending on those factors there will be a change in the frequency stability of an oscillator. Next we will talk about the condition for oscillation. So frequency feedback amplifier generally consists of two parts. One is an amplifier and second one is a feedback circuit. The feedback circuit usually consists of resistors. The concept of feedback amplifier can be understood from the following figure. From the figure, the gain of the amplifier is represented as A, and the gain of the amplifier is the ratio of output voltage into the input voltage, that is V0 upon Vs. The feedback network extract a voltage which is given by, that voltage will be a feedback voltage Vf, which is given by beta V0 from the output V0 of the amplifier. This voltage is added for positive feedback and subtracted for negative feedback from the signal voltage Vs. That is that means what our output will be V0 equal to Vs minus Vf or Vs plus Vf. Now let's just take a minute and try to answer these questions. One condition for oscillation is what? It is the first condition. Feedback circuit consists of what? And for an oscillator to properly start, the gain around the feedback loop must initially be what? hope you got the answers. So one condition for oscillation is a phase shift around the feedback loop of 0 degree. Next, feedback circuit consists of resistors, and for the oscillator to properly start, the gain around the feedback loop must initially be greater than 1. So these are the answers C, A, B. Now let's just move forward. So I will continue with the condition for oscillation. So for a positive feedback, Vi equal to Vs plus Vf, which is also can be written as Vs plus beta V naught. Beta V naught is nothing but the Vf. The quantity beta equal to Vf upon V naught is called as feedback ratio. That is, how will you find it out, beta? So if you take down the V naught to the left hand side, to the denominator, then it will become Vf upon V naught, and this beta is nothing but a feedback ratio or feedback fraction. The output V naught must be equal to the input voltage, that is Vs plus beta V naught, which is multiplied by the gain A of the amplifier in order to find out the output voltage. So for the positive feedback, input voltage is Vs plus Vf, and it will become Vs plus beta V naught. But if you want to find out the V naught, then output will be Vs plus beta V naught into A, that is, we have multiplied the gain. Okay, now if you remove the bracket, then it will become AVS plus A beta V naught equal to V naught. Now this V naught terms comes to the right hand side, then it will become AVS equal to V naught into 1 minus A beta. Now this equation will become V naught upon Vs will become A upon 1 minus A beta. Let AF be the overall gain of the amplifier, that is gain with feedback. This is defined as the ratio of output voltage V naught upon to the applied input voltage Vs, that is V naught upon Vs will nothing but the AF. From the above two equations, we can understand that the equation of gain of the feedback amplifier with the positive feedback is given by AF, that is V naught upon Vs is AF. So instead of V naught upon Vs, we'll write on AF equal to A upon 1 minus A beta. So where A beta is the feedback factor of the loop gain. Now if A beta equal to 1, then the denominator part will become 0. Then the whole AF will become infinity. So thus the gain becomes infinity, that is, there is output without any input. In other words, the amplifier works as an oscillator. But if in this condition A beta equal to 1 is called as Barkhausen's criteria of oscillation. Now we'll talk about the classification of oscillator. So oscillators are divided into two types, sinusoidal and non-sinusoidal. Now sinusoidal oscillators are divided into two types, that is RC phase shift and crystal oscillator. Here in this lecture we'll only discuss about the sinusoidal and non-sinusoidal. In the next lecture we'll start with the RC phase shift oscillator. First we'll talk about the sinusoidal oscillator, or it can also be called as sine wave oscillator. An oscillator is an electronic circuit that produces a periodic signal. If the oscillator produces sinusoidal oscillation, it is called as a sinusoidal oscillator. It converts the input energy from a DC source into an AC output energy of a periodic signal. This periodic signal will be having a specific frequency and amplitude. The block diagram of a sinusoidal oscillator is shown in the following figure. The block diagram of a sinusoidal oscillator shown here produces sinusoidal oscillations when the following two conditions are satisfied. First, the loop gain A beta of the block diagram of sinusoidal oscillator must be greater than or equal to unity. Here A beta and AB and beta are the gain of the amplifier and the gain of the feedback network. The total phase shift around the loop of the above block diagram of a sinusoidal oscillator must be either 0 degree or 360 degree. The above two conditions together are called as Barkhausen's criteria. Next, we will talk about the non-sinusoidal oscillator. The oscillator that produce an output having a square, rectangular or sawtooth waveform are called non-sinusoidal or relaxation oscillator. It does not provide you any sine waveform. Such oscillators can provide output at frequency ranging from 0 Hz to 20 MHz. A non-sinusoidal waveform is typically a periodic oscillation. Figure shows a pulse train. So this figure shows a pulse train. It is a stream of pulses at regular intervals. Means each pulses are equally spaced. A pulse may be defined as a voltage or current that changes rapidly from one level of amplitude to another level. It is an abrupt discontinuity in voltage or current. These pulses are extremely used in digital electronics. Now let's just take a minute and try to answer these questions. If A beta equal to 1 and AF equal to infinity, then if A beta equal to 1 in the equation A upon 1 minus A beta, then what will be the value of AF? The value is given as infinity, whether it is true or false. A non-sinusoidal waveform has a dashed oscillation, and in positive feedback both input and output are what? I hope you got the answers. So if A beta equal to 1, AF equal to infinity, this answer is true. A non-sinusoidal waveform has a periodic oscillation, and in positive feedback both input and output are in phase with each other. So these are the answer A, B, B. I hope you have understood the concept of condition of oscillation and classification of oscillator. Thank you.